Thank you very much. I'm Hikmatullah from Kingston University. I'm in my final year of PhD, and today I'm going to be presenting my research, which is regards to strengthening of slab-column connection against punching shear failure with fiber-reinforced polymers. Just to give a bit of the background about the problem, flat slabs have been widely used since the past century due to its numerous functional and economic advantages. However, the slab-column connection is one of the most critical D regions in an RC structure due to complex state of stresses present specifically in this region. The combination of locally high bending moments and shear forces at this connection increases its sensitivity to brittle punching failure. In this failure mode, the slab collapses around a truncated cone over the column, which may eventually lead to progressive collapse of the entire building. This failure mode is often the governing failure criteria in flat slabs. On the right-hand side of the slide, we see failure of the Piper Row car park in Wolverhampton. The failure initially started by failure of one of the connection, and then it led to progressive failure of the entire flow. In the recent past, tragic examples of such cases have increased the general awareness, and research has been done to address this issue. With this specific case, the main issue was shorter anchorages in combination with corrosion of the flexural reinforcement, which led to failure of this connection, the slab. The number of aging structures are increasing. There are similar structures as to Piper Row car park which are in need of retrofitting. The strengthening is often needed due to corrosion of reinforcement, probably due to freezing and thawing attack, chloride-induced penetration, or fire damage, or there could be a whole lot of other reasons which will require strengthening. The strengthening is often needed to increase or to restore the initial design capacity. The existing methods for improving the load-carrying capacity of flat slabs are steel plate bonding, provision of column drop, and section enlargement. However, these methods are elaborate, expensive, and are intrusive to the structures. FRP materials have been studied over the past 2 decades, and it fulfills the shortcomings associated with the current strengthening techniques. So why should we use FRP? FRP composites have been successfully used and applied in the field of mechanical and aeronautical engineering. It has evolved these industries, allowing for production of more lightweight, efficient, and reliant components. FRP composites possesses significantly high tensile strength in steel reinforcement, and mainly its corrosion resistance, which could be one of its major uses in the marine environments. Fiber reinforced polymer composites are made of fibers, very high tensile strength, inside a polymer matrix. A typical stress strain graph for the FRP materials are shown over there. Generally, there are 4 materials available: carbon, glass, aramid, and basalt. All of them have different properties in terms of its tensile strength, carbon being the highest, and AFRP and GFRP being somewhere in the middle. And you can see, as comparison to steel, it is significantly higher. For this research, we have gone and chosen CFRP reinforcement for strengthening purposes, primarily due to its high tensile strength. Currently, there are design guidelines for strengthening of existing structures, but they do not cover strengthening of flat slab junctions with FRP materials being strengthened with it. And there is insufficient experimental data to support the development of codes in this area. The experimental program that we have conducted, a total of 12 slabs were tested. 9 of them were strengthened with FRP materials. 3 of them were acted as control sample. They were square slabs with dimensions of 1.5 by 1.5 meter, with a thickness of 120 millimeter, and a central column of 150 by 150. All of the reinforcement, the slabs have identical geometrical layout, and the reinforcement were similar. They were designed to fail under punching shear. We use 2 strengthening methods. The strengthening methods that we use are externally bonded reinforcement and near surface mounted. reinforcement. And the externally bonded reinforcement method, FRP laminates are attached to the tension surface of the slab using epoxy adhesive. And these are basically acting as flexural reinforcement, which will indirectly increase the punching shear capacity of the slabs. There have been some previous studies in this regard, but there is a major concern with external strengthening with FRP. The premature bond failure FRP from the substrate, which is the concrete, is one of the major issues. Before reaching to its maximum level, when it reaches a load of up to 70 to 80% of its maximum allowable capacity, it debonds from the surface of the concrete. So that was one of the main concerns of this research that we have addressed. In order to address this issue, we have introduced something that's called transverse anchorages. So in this first set of experiments, there were 4 slabs. So one was controlled. The second one was strengthened with FRP, 50 millimeter wide laminates with 1.2 millimeter thickness. At the bottom, 2 of the samples, the transverse anchorages could be seen. The reason for selection of these anchorages were, initially we tested slabs in order to find the strain profile inside the concrete. And when we measure that the strain is very high towards the center of it, and it exponentially decreases as we are going away. So potentially by placing these transverse anchorages, because the strain is very low, the debonding will not occur at those specific regions at lower stages of the loading. And based on most postulate, because these are acting as flexural reinforcement, it will be contributing to the punching capacity. The second method that we used was a near surface mounted method. In this method, grooves are created inside the concrete and FRPs are attached with using epoxy adhesive. The remaining cavity is then filled and leveled. The major advantage of this method as compared to externally bonded method is, initially we did some testing of bond test, and this was found to be more than 200 to 300% stronger bond strength as compared to EBR. They have increased fire resistance because the FRP is protected inside the concrete, and it's aesthetically pleasing, specifically in the region of the car parts where there is the negative moment. It will be protected against the accidental damage from the cars and the tires damage. So we use 2 strengthening layouts, layout number 1 and layout number 2. In layout number 1, we have 2 reinforcement in each direction, and layer number 2, we have 4 reinforcement in each direction. All of these reinforcements were additionally added after casting. They are made of carbon fiber reinforced polymers. In each layout, we used 6 millimeters, 8 millimeters, and 10 millimeters rebar. They are positioned specifically in the region affected by punching shear. The instrumentation was we used a number of LVDTs at the mid-span, quarter span, and at the end of the slabs to measure the deflection. A number of strain gauges were attached to the tension surface of the concrete, to the FRP reinforcement, and also strain gauges were attached to the steel reinforcement to measure the yielding of the steel reinforcement. We developed this testing rig to test the slabs. The load was applied from the bottom. As you can see, the boundary conditions, they were free to rotate by placing smooth surface rebars. Steel angles were placed, but they were showing some level of deformation, so we measured its deformation by positioning dial gauges, and we take this into consideration during our analysis. After the testing, all of them were tested under punching shear failure until the failure point. So with EBR strengthening method, this is the load versus deflection graph. The control sample failed under punching shear once it reached a load of 175 kilonewtons. As expected, the second sample, once it reached load of over 150 kilonewton, because it did not have additional transverse anchorages, it debonded, and then it reacted in a very similar way to the control sample, so it didn't actually contribute to increase in strength. With the 2 other samples, which were using two different type of transverse anchorages, we can see considerable increase in the stiffness and in the ultimate load. If you can see, there is a drop after reaching to the maximum load. It's showing failure of one of the anchorages. So by placing 2 anchorages next to each other, we are gaining additional strength. We are describing this as residual load, so it will be used as a warning sign. So once the sample fails, the first anchorage fails, the people can vacate the building and it could be restored. The load versus strain graph is shown on the left-hand side of the slide. We didn't reach maximum capacity of the FRP. It reached up to around 25 to 30% of its rupture strain before failure. With the near surface mounted method, as we can see, it maintained a very strong bond with the concrete. No debonding occurred during the failure. As we can see, the considerable increase in ultimate load could be obtained with strengthening layout number 1 because it had only 2 FRP reinforcement in each direction. On average, it increased the load by up to 18%. With the strengthening layout number 2, on average, it increased the load by up to 41%. So the amount of increase in load and its stiffness is directly proportional to the layout and to the number of reinforcement available placed in the slab. With the load versus strain graph is shown, so the strain level is much higher as compared to the EBR method, which contributes to the increase in load. So these experiments are compared with the design codes. The design codes do not provide definitive guidance for strengthening of the strengthened slabs, but we use a method developed initially by Shen and Lee. It basically introduces 2 new terms, which is called effective depth and effective reinforcement ratio, which are equivalent values. Failure occurs when the concrete reaches a strain of 0.03 or when the FRP rupture occurs, whichever comes first. So the CFRP acts as a additional reinforcement. The detailed calculation is shown over here. So we will be introducing these 2 new terms, and these will be swapped in the design codes, the D equivalent and rho equivalent. The experimental values were compared against the ACI, Eurocode and Fed model code. So these values were changed. As we can see in the ultimate load comparison, the design codes predict the ultimate capacity very accurately for the non-strengthened cases. These samples and strengthening layout number 1, both of them increase the ultimate load quite significantly. But when we are making the comparison with the design codes, when we take the effect of the strengthening into consideration, it actually provides a rough guidance of what the failure load would be. So by using the modified method, we are actually predicting the maximum strength of the strengthened samples. And the Eurocode 2 was the most efficient out of all of them. The reason is because it takes both the effect of effective depth and a reinforcement ratio into consideration. The ACI and the Fed model code does not take the amount of reinforcement into consideration. That's the reason their predictions are more conservative. To sum up, both methods, EBR and NSM, could be used to increase the ultimate load of the average load increase was 25% and 44% for EBR and NSM. The EBR system, we are retaining up to 90% of its residual load, which is basically the drop in the ultimate load deflection curve. All of the samples displayed very high level of stiffness, and by modification of the code and introducing new terms into the design code, we can actually predict the capacity of strengthened samples. Thank you very much.